Ask an AI to build real-time GPS tracking and it will generate an HTTP polling loop clean code. Correct logic. At 10 users, it works perfectly, but this is exactly the problem Zepto solved when scaling to millions of orders. At 100,000 concurrent users, that code generates 10 million requests per minute, 90% of them returning no new data. The system collapses. In the next 8 minutes, you will learn the WebSocket architecture Zepto actually uses and why it is the decision that keeps the one engineer in the room employed. 5 things you will own after this video. The mathematical proof of why polling fails at scale. The WebSocket upgrade handshake that creates the channel. The dual client routing logic. The reconnection storm failure mode. Most engineers miss and the survival skill. The exact judgment call AI misses when designing real-time systems. Let us build it. Here is the AI default HTTP polling. Your app asks the server, where is the order? The server queries the database, no change. It returns the exact same GPS coordinates it returned a second ago. 1 second later, your app asks again. The server queries the database again. Still no change. This sounds harmless until you multiply it. 100,000 active orders, 100,000 queries per second, every second. At second 3, the database CPU hits 100%. The entire system crashes. And the worst part, 90% of those queries returned zero new data because the delivery partner was stopped at a red light. This is what happens when you let an AI default to HTTP for real time. Now let us look at the architecture Zepto actually uses. The correct architecture starts the exact same way, an HTTP request. But the customer app includes a special header, connection upgrade. It is asking the server to change the rules of the conversation. The API gateway sees this header and routes the request to a dedicated WebSocket server. This server's only job is holding open connections. The WebSocket server replies with HTTP status 101, switching protocols. The handshake is complete. The connection does not close. It is now a persistent bidirectional pipe. The server can push data to the phone at any moment. No more polling. This sounds like a limitation. It is the opposite. Holding a connection open takes almost zero CPU. It just takes a few kilobytes of RAM. A single WebSocket server can hold a million open connections easily. But how does the server know what data to push? That is the next piece. Both the customer app and the delivery partner app have performed the upgrade handshake. They are both holding open WebSocket connections to the server. But how does the server know which connection belongs to which order? It stores a mapping in Redis. Order ID maps to connection ID. The delivery partner's phone moves 10 meters. It pushes its new GPS coordinates up its open WebSocket connection to the server. The WebSocket server receives the coordinates. It asks Redis what is the connection ID for the customer watching this order. Redis replies instantly. The server pushes the new coordinates down the customer's open connection. The dot on your screen moves total latency under 50 milliseconds, zero polling, zero wasted database queries. Now I want to show you the one failure mode that destroys this perfect design. Here is the judgment call most engineers miss until it takes down their system. You have 100,000 active WebSockets. Suddenly, a mobile network provider drops connection for 10 seconds. All 100,000 WebSockets sever simultaneously. 10 seconds later, the network returns. Every single mobile app runs its reconnection code at the exact same millisecond. 100,000 concurrent TCP handshakes hit the API gateway. We call this the thundering herd. The gateway CPU spikes to 100% and the entire system crashes. How do you fix it? You don't fix it on the server, you fix it on the client. You add exponential backoff with jitter. Instead of reconnecting instantly, the app waits a random amount of time between 1 and 5 seconds. The 100,000 requests are now spread out over 5 seconds. The server survives. That is system design. Let us look at the trade-off table. HTTP polling sends heavy headers, cookies, auth tokens every single second. WebSocket sends a few bytes of binary data, over an already open pipe. Polling delays the update until the next scheduled question. WebSocket pushes the update the millisecond it arrives. I will write the polling loop because it is easier. The engineer builds the WebSocket because they know what happens at 10,000 users. You have seen every layer and every trade-off. Let us put it all together one final time. The full system in one clean view. Let us put it all together. Hop 1. Customer app upgrades to WebSocket. Hop 2. Partner app upgrades to WebSocket. Both connections are held open by the server. Hop 3. The WebSocket server maps both connection IDs to the single order ID in Redis. Hop 4. The partner app pushes new GPS coordinates up the open pipe. Hop 5. The server instantly pushes those coordinates to the customer. Zero polling, zero database queries. You now own the architecture. Real-time architecture is the gap between a developer who queries a database and an engineer who designs a channel. Before this video, if someone asked you how to build real-time tracking, the answer was just query the location every second. After this video, the answer is polling collapses the database at scale. You must use a WebSocket for a persistent bidirectional channel, and you must protect the gateway with exponential backoff on reconnect. That distinction is your job security. Next Tuesday caching. Zepto uses Redis to serve 10 million inventory requests a day. What happens when a product isn't in the cache? The cache stampede. It is the exact failure mode AI ignores. See you Tuesday. Subscribe to ByteLearn for the complete One Engineer System series, one survival skill every Tuesday. Hit the bell question. Have you ever accidentally dedosed your own server with the polling loop? Be honest in the comments.